In this video, I'm going to take a vector field. I'm going to determine whether or not it's conservative. And if it is conservative, we're going to find a potential function for it. Here I've taken this polynomial vector field. It's 3x squared y squared plus 2. And then I have 2x cubed y minus 12y cubed. F is defined on the entire plane. And the plane itself is a very nice region. It is open, it is connected, and it is simply connected. So the theorem that we discussed is valid. If I compute the curl and I see that the curl is 0 everywhere, I will know that my vector field is conservative as a result. So let's compute the curl. I'm going to have to take the partial derivative with respect to x of the j component and the partial derivative with respect to y of the I component. So put those in. And compute the partial derivatives. When you do this with respect to x, you'll get 6x squared y. That will be 0. Compute this with respect to y. You'll get 6x squared y, and this term will be 0. And those get subtracted. Look at this. Despite the fact that the derivatives were kind of complicated, after I differentiated and compared the two, I got the same thing, and therefore it is curl-free on the region. Everywhere, at every point on the plane. As a consequence, from the theorem, f must be conservative on the entire plane. This begs the question, what is a potential function? F must be the gradient of something. How can I go about and find a potential function? To do so, I'm going to state the requirements that this potential function should have. Its partial derivative with respect to x should be my I component, what we call m. So phi x must be m, which we know, we're given this. And similarly, the y component should be n, which is this other polynomial expression. I'm going to take one of these quantities here. I'm going to take phi x, and I'm going to integrate it with respect to x to undo that partial differentiation that we did to get this result. So let's take phi of x and integrate it with respect to x. Basically, I'm integrating m, my I component. In this case, I have 3x squared y squared plus 2, and I integrate it with respect to x. Anything involving an x will go up a degree. So I get x cubed y squared now, and any constant term becomes linear plus 2x. Now I'm integrating, so I should get a constant of integration. But here, constant means anything that doesn't have any x's in it. Because when I differentiate with respect to x, if I get 0, it might have been that I had an expression that had a number like 7 in it, or it could have been something that had only a y in it. So when we say constant with respect to x, I mean a function that could potentially have anything involving y, just as long as there's no x's in there. The partial derivative of fy here, some function of y, will be 0. So phi is almost determined. It must have this term, and yet some mysterious term involving y. Those are the constant terms. To figure out what could be there, what I'm going to do is take advantage of the other criteria that the y derivative must equal this. So I'm going to take my result for phi and I'm going to differentiate it with respect to y. In this case, I'll get 2x cubed y. The 2x term will become 0. And I don't know what f of y is, but its derivative with respect to y will appear here. I know what the result is supposed to be. It's supposed to be equal to n. That's supposed to be my other component, so I start to compare these two and I line up the terms. I see this 2x cubed y in both of them. Here I see the f prime of y, and here I see minus 12y squared, or y cubed rather, and so it must be that this term and this term are the same. Our conclusion is that f prime of y is minus 12y cubed. To find f of y itself, I integrate that with respect to y, because it's a function of y. And integrating that, you get 3y to the 4th, and potentially you could have any constant here. And when I say constant now, an honest constant like 7 or pi. Nothing involving x's or y. So putting it all together, phi is this function with f of y now determined to be this expression. these are all the potential functions that could possibly work. I'm taking these terms plus what we just discovered f of y to be. The potential is something of this form where c can be any constant. Choose any constant you want, and the gradient of that function phi will be my original vector field f that you can quickly check by taking the partial derivatives of phi and comparing them with m and n.